All right, so let's get started. Let me get the sign-in sheet passed around. We're starting to get kind of close to where we need to think about a celebration. Remember, we don't have exams in college, we have celebrations of learning. So we need to start thinking about celebrations. I was looking at our schedule, our tentative schedule, and we're actually pretty on, in terms of our lecture topics. And of all the classes I teach, this is the one class where I tend to hold to the schedule pretty rigidly, because for a deformable class, I hold to the schedule pretty rigidly. I didn't even mean to do that one. That one's pretty good. Let's talk about that. So I have the exam scheduled for Thursday, September 25th, okay? And so just right off the bat on my announcement slides, this is going to stay up here, okay? So, no, Tuesday, September 25th. Why did I say Thursday? The exam is scheduled for Tuesday, September 25th, okay? That box is going to be on every announcement slide from here on out, so that you're going to see a reminder like every day. That extra parenthesis is going to bug me. I need to get rid of that if PowerPoint would decide to cooperate with me. Sorry. All right. Sorry. Okay. So just so you're aware, I do my exam review sessions a lot like I do homework. On Thursday, September 20th, I'm going to come in, and all I'm going to do is, at the very beginning, for about 5 or 10 minutes, I'm going to talk about the exam. I'll go through the format of the exam, what to expect, what not to expect, what's going to be covered on it, so on and so forth. And then I shut up and let you all ask whatever you want on Thursday. So Thursday could be a 10-minute lecture, or it could be a 75-minute lecture. It depends on the questions you have. I want you going into the exam to feel comfortable, okay? So ask whatever you want. Like I said, you can ask anything. You can ask what the answer to number 2 is. I'm not going to tell you, but you can ask. Like, there are certain things I'm not going to say, but when it comes to what we've covered in class, whatever you want's on the table. So that'll be on Thursday, and that's all we're going to talk about on Thursday, and then Tuesday we come in and take the exam. Now, in terms of other housekeeping, we do have a homework that's due on Thursday, okay? Once you turn that in, I'm going to assign you homework number 3, which is the homework on torsion. I'm giving you a week on that assignment. I've given you like a week and a half on the others, but this assignment is short, so it's not so bad. Everybody okay with this moving forward? All right. Let me just search up, because I think by now the schedule's pretty clear. Let's talk about homework number 2. It's due on Thursday. Does anybody have any questions on it? Everybody good? Okay. All right. So again, that's due Thursday. One thing I'll mention, and I'll go ahead, I think I have my next announcement slide up. I'll go ahead and even show you if I can. Is it? All right. So I'll go ahead and show you. This is going to be on Thursday. You're going to submit homework number 2, and then I'm giving you homework number 3. Now, one thing about homework number 3, it's due on the 20th, okay? Now, because this is going to be on the exam, what I do for that homework right before the exam is the moment that you turn it in, I give you the solution, okay? I do that so you have something to study for the exam. Like, I'm not going to be able to just, immediately grade it like that, but I want to give you something to go off of. So, but here's the caveat. Because I'm giving you the solution the moment that you're turning it in, I can't really accept late submissions because you'll have the solution. You see what I mean? So I'm telling you that now, so just so you're aware. Everybody good? Okay. All right. Well, let's talk about torsion, okay? Because this is a pretty important concept. Hold on. Is my remote going to work? There we go. It's a pretty important concept. I'm going to go ahead and be honest and say that I think this is going to apply more to the mechanical engineers in the room than the civils. We civils try and avoid twisting as much as possible, but you mechanicals, sometimes you can't get around it. Like if you have a drive shaft in a vehicle or something like that, any element in a machine that's going to be twisted, you got to handle torsion. It goes very naturally after axial loads because, as you'll see, the formulas are very, very simple. Now, one thing I'll go ahead and preface this. I got a little bit of a derivation coming up. There's going to be some some calculus peppered in there, but I want you to rest assured that at the very end of my derivation, I have a nice couple slides that summarizes all the formulas you need to know. So it's all right there. Because I know you're like, okay, we get it. We just want forms. but in all seriousness, I do think that there's a couple points to glean from this derivation, because there's some really interesting points, not just from the math, but from a design perspective. And we're going to hit on that here in a little bit. Now, like I said last time, when we're talking about torsion, one of the things that we will never consider in this class is torsion of a shape that is non-circular. In other words, if it's a pipe or a shaft, a circular shaft, it's fair game. Anything else? No. I'm not going to ask you. And honestly, as a mechanical engineer or even a civil engineer, if you've got torsion, you're going to want it to be applied to a circular cross-section anyways. I brought this to kind of explain. I mentioned that non-circular cross-sections warped, and I think this will give you a really clear idea as to what that means. Okay, what I'm going to do is I'm going to hold this one end fixed, like I'm going to clamp this, and I'm going to take the other end, and I'm going to kind of twist it. If you look, like sort of like a helicopter looking right on top of the I-beam, what you're going to see is a couple things. Obviously, you see that it has rotated, like I've taken the I-section and I've turned it. But if you look at like the flanges, the little tips right here, if you look at it before and like after twisting, you're going to see the flanges like they move in and out. Okay, that's what warping is when it moves, when it deforms in and out of the cross section. So think if you're designing some mechanical system and you have this connected to this and you twist it, you're going to want that section to be circular, because if not, it's going to jut up against whatever it's next to, and that's going to cause some stresses you didn't intend. I'm going to pass this around just so you all can see that. Like if you go like this and twist, you'll see what I mean, that the flanges, they go in and out. So there you go. Don't hit the student next to you with it, please. Let's talk about the math a little bit, and let's get into the derivation. So what I've got here is a circular shaft, and it's being subjected to torsion. Now, when it comes to the assumptions, like we're making a few assumptions here. Number one, the total length of the shaft remains unchanged. So before and after, like if I take a circular shaft and twist it, it's still the same length. Now that actually wouldn't be applicable to an axially loaded member, because if you take a member and you yank it, it gets longer. But that's not the case with twisting. If you take an element and you twist it, it's just going to rotate. We also assume that circular cross-sections remain circular. So before and after, it's still a circular. Which for circular cross-sections is a very reasonable assumption. Now, before and after twisting, what you get is you get a, if you were to like draw a big grid on a circular shaft and apply a torsion, you would see that before and after, like here's my element before and here's my element after. And really what's happening is you're getting an angle change. Like that shearing strain, that's just a change in angle. So that's really what we're going to be after. Okay, so I want to see if I can define that angle change, and let's see where we can let's see what we can do with that. All right, so through differential calculus fashion, what I'm going to do is I'm going to cut out a little segment of this shaft. You know, it's like when you're first learning how to integrate and differentiate and stuff like that. You probably remember being introduced to that term dx. You know, that little slice of that function. Well, here we're going to look at a little differential slice of this shaft. So we're going to cut out a little disc, and we're going to investigate a little chunk of this shaft. So just so you're aware in terms of the variables, when I refer to the term x, I'm talking about x along the length of the shaft. So when it's all said and done and I need to determine the total response, I'll, for instance, integrate from x equals 0 to x equals L. Now, x is refers to the length of the shaft, whereas this term rho is in regards to the circle, if I was looking at the cross-section. So rho is basically going to be my variable related to the radius. So rho is going to go from rho equals 0 to rho equals r. And when I say rho, I'm talking about this funky looking P here. That's a Greek letter rho. So everybody okay with that? If you go to the canoe, the concrete canoe over there, our first canoe at Marshall, we always named the canoes, and they had row, row, row your boat. That was the name of the canoe. So it's over there in the old engineering building. You ought to check it out. Pretty funny. All right. Okay. So I want to look at that little. So what you're seeing here, this is, we're cutting out a little slice, a little disc of this shaft, and we're investigating this little wedge. This is before and after. So the left is right before we apply that load, and the right is after. Okay. Now what we're seeing on the right is a change in angle. Okay. So this change in angle right here, that's the shearing strain that we're after. So that little funky looking Y, that's gamma. Okay. So what we're after is that shearing strain gamma. In order to define a couple other things, there's not only do we see a shearing strain gamma, we also see a change in angle phi where the section is rotating. Okay, and ultimately I'm going to define both of those, but I just wanted you to be aware. Now, what I'm going to do is I want to see if I can relate those two. So what we've got here is it might seem a little complicated. It's really not. Let me go back to a pretty basic definition. If you have, like a graph, and you have a graph of let's say a circle, that's the best circle you're going to get out of me, okay? All right? And let's say that circle has a radius r, okay? And let's say I have some angle theta. How do I determine how long that arc length is? It's r times theta, right? That's pretty basic trig, or pretty basic geometry. So I propose that this arc length S right here, the arc length S, is angle times dx, or that angle times rho. So we're sort of able to relate the angle up top and the angle on the bottom through some pretty basic geometry and some pretty basic trig. So if I compute, or if I solve for gamma, if I solve for that strain up top, which is really what I'm after, I'm trying to determine the shearing strain. Maybe I should delve into that. Why do I care about determining gamma? Well, if I can determine the shearing strain, I can determine the shearing stress. And stress is what we're all after in this class. What I get is that gamma equals rho times however fast that internal angle is changing, the rate of change of that angle. Is everybody okay with that? Okay. Now, that might seem like, who cares? Like, okay, great, wonderful. Good job, Dr. Mike. We don't really care. But there's a couple behavioral observations that are really important for a design engineer, okay? What this tells us is the following, okay? Remember, this rho, that's a variable, okay? Remember, rho goes from rho equals 0 to rho equals r, right? So rho goes from at the center being 0 and at the edge being the maximum. So I want you to think about that. As rho gets bigger, would you agree that the strain gets bigger? Is everybody okay with that? Just from a formula perspective. Okay, now, if you agree with that, think about this. What that means is that if here's my circular shaft, at the very, very center of that shaft, if I'm twisting it, there's no strain, okay? And if there's no strain, what's in the center? If there's strain, there's no stress, okay? So from a torsion perspective, if you take a circular shaft and you apply torsion, you get 0 stress in the middle at all, okay? Whereas on the outside, on the walls, on the outer edge of the shaft, that's where you're getting your maximum stress, okay? That's really important, okay? Because, okay, let's say you're designing, if you've got some, some element that's subjected to torsion and you're a design engineer, honestly, what really matters is what's going on the outside, right? The outer wall, okay? If the outer wall, if you're designing that shaft subjected to torsion and the outer wall is fine, then everything else is fine. Make sense? That's important from a design engineer's perspective, because as a designer, all you need to care about is the stress on the outside. In fact, if we were trying to plot the stress it would look like this. Now, I mean, you know, here at the center, we would have 0 stress, and then at the edge, we would have our maximum stress. Now, we don't know what tau max is yet. We got to derive that. But in the end, that's what we're trying to derive. Does that make sense? That's important from a design engineer's perspective. So, bless you. And we're going to make similar observations about that for a variety of different things that we design. Like when it came to axial members, if you have a constant load, then you know the stress is the same everywhere. If you've got a member subjected to torsion, you know you need to only check the stress on the outside. Those little nuggets of wisdom are really, really important that'll help you out later in your career. So this is some pretty important stuff. So what I've got here is I've got a circular shaft. Again, rho is a variable that goes from the center all the way out to R. And I propose that my stress function is going to be proportional. So it's going to go from rho equals 0 and a stress of 0 to rho equals R and some maximum stress. So this equation right here, all this is y equals mx plus b. That's all this is. The y-intercept is 0 because at rho equals 0 we get no stress, and at rho equals r we get tau max. So that's all that is. That's y equals mx plus b. So the slope being change in y over change in x, and that's your x if you want. Everybody good? Okay. Now, if you understand that, everything else that I'm about to do is actually going to be pretty straightforward. Okay? I'm going to use another calculus philosophy. I'm going to cut out a little slice, and then I'm going to integrate. Okay? And let me show you how that's going to work. So I'm going to cut out a little slice of this, this shaft, so this little shaded region here in the middle that's sort of D rho thick. Okay? I'm going to do that. And if I can determine the force and the stress and the torsion here and then integrate, that'll give me the torsion overall. So let's see how that works. First off, let's look at this little ring. Okay? How would I determine the area of that ring? Well, I propose we would just take the circumference multiplied by the thickness. Everybody okay with that? So what's the circumference? 2 pi times the radius, which in this case is rho. And then the thickness is this little d rho, that little differential thickness, right? Everybody good with that? Now, if you're okay with that, if that's the area and the stress is tau, you know, how do I determine the force? Well, it's the stress times the area. So what I'm using for stress is this tau function that I got here. And I'm going to plug and chug and expand this out here in a second. So the force is the stress times the area. And if I know force, how do you determine moment? Or in this case, the torque. Well, it's the force times whatever your moment arm is. Does that make sense? So in this case, this d torque, the torque is the force times the moment arm. So all I'm going to do is ultimately I'm going to integrate this right here. I'm going to integrate that. And in order to do that, I'm just going to say, okay, well, df equals that, and then that equals what I had on the previous slide, and just chug it out. So again, I think this part's actually the easier part to follow. So let's chug that out and let's see what we get. So here's my equation for stress. Here's my area of that little slice. So how do I get force? It's stress times area. So this is just me multiplying those two and just chugging it out. As for the torque, I take this times rho. And so all you're seeing on this slide is just me carrying out the algebra. Is everybody okay with that? It's at this point, it's just a little bit of alphabet soup at this point. So far, so good? You want me to leave this up here for a sec? That's fine. Excuse me. Everybody good? All right, okay. So what I'm going to do is this, okay? I'm going to take this, what this is telling me is how much torque I'm applying to the section. What I'm going to do is, but this is torque to that little differential element. So I'm going to integrate that, and I'm integrating that over the area. So I'm basically integrating from rho equals 0 to rho equals r. I'm integrating over that whole disk, okay? And so what I get is I get this. I get three things. I get tau max, okay, which I'm trying to figure that out. I get R, which I know what R is at the beginning. R is the radius of that shaft. That's the constant. Like if it's a 4-inch diameter shaft, I know that R is 2 inches. Like that one's easy. But then I get this. Okay, let's talk about that in a second. Now, if I solve for tau max, I get this. Okay, so let's look at this expression. I get the R, which is again what I know. I know the radius of the shaft. I get the torque, which you would think at the beginning that's something that you would know. I mean, the purpose of this derivation is to say if I have a shaft and I twist it with 100 foot-pounds of torque, how much stress do I get? So torque is something I would know at the beginning. Tau max is what I'm trying to figure out. So I know the torque, I know the radius, but then there's this. Like, what's going on with that? Well, if you take a sharp look at that integral, you've got the integral of 2 pi from the integral of 2 pi, so it's 2 pi times the integral. We have rho equals 0 to rho equals r of that. Now, I have that sort of highlighted in and of itself because I'm calling that a section property. And what I mean by section property is that is a property of the shape of the shaft. So if here's the shaft and I'm looking at the shaft, that is a property of the shaft because it's an integral from rho equals 0 to rho equals r of that, in this case, radius cubed. Just that function. So that has nothing to do with any stresses or how long the shaft is or anything like that. It is just a property of that section. Okay? And section properties are a really important point, not just of this class, but what you do as engineers. We've already been exposed to section properties already in here. One of the most important section properties that we've been dealing with all semester is areas, right? You samurai sword or lightsaber through a section, we needed to know the area. And that was really, really important to us when we were looking at stresses and axial loads because the bigger the area, the less the stress, right? And that told us a lot about what was going on. Well, for our purposes, this is another section property. We're going to call this section property J. J stands for what's called the polar moment of inertia. So your books, like I call it J, sometimes your book might call it I sub P. Like I said, if you ever see I sub P or J, it's the same thing. But J is a property of cross sections that we're going to use that's going to be appropriate for us for torsion. So the idea is that if you're looking at your shape, the higher your J value is, the lower your stress. Okay? Here's why that's important. Okay? Here's why that's important. Here's why section properties play such a big deal in engineering design. So we can compute J pretty easily, and I'm going to show you how we do that here in a second. If you have J for, let's say, just a circle, okay, well, I'm integrating from rho equals 0 to rho equals r. Well, this is a pretty easy integral. What's the integral of rho cubed? It's rho to the 4th over 4, right? Plug in r minus plug in 0 and plug in chug, and you get this, right? J is pretty easy to define, and this is a slide that I might want to write down. This would be a J value for a solid circular shaft. This would be a J value for a pipe, okay? So the difference is that for J for a solid shaft, it's just pi r to the 4th over 2, and for a pipe, it's the outer circle minus the inner circle. Okay, this is something to write down, and this is really, really important. Let me give you all a second on this because this is all right. So here's why section properties are so important. We've been using A earlier, now we're looking at J. If I'm an engineer and I'm assessing the condition of a drive shaft in a car or whatever, it doesn't matter, and I look at the stresses and I find the stresses are too high from a mathematical perspective, if my section property values go up, my stresses go down. Like, and that's, I mean, just look at the equations. I mean, if J gets bigger, this gets smaller, right? Okay, well, if here's a circular shaft, how do I make A larger. I make that larger, right? So section properties are just our mathematical way of expressing the performance of a given component. If I'm designing a shaft subjected to torsion and I find the stresses are too high, I need to make it bigger. And that's what J is telling me, is that J needs to be bigger. So as a design engineer, one of the things you might do is solve for J. Figure out what J you need in order to safely resist some loads, and then pick a shaft that has the appropriate J value. Does that make sense? Okay, all right. That's a really important, observation to make. Now, like I said, we are never going to deal with anything that's non-circular. So these are the only two J values you're ever going to deal with me this course, this semester, period. Either J for a shaft or J for a pipe. Now, a couple things to point out, and I'm going to summarize all these formulas in a bow for you here in a second. Number one, remember that stress and strain are proportional. Now, we've been using for a while sigma equals E times the strain. Well, that's for normal stress. That's for taking something and yanking on it. Here, we're taking something and twisting it. So from a stress perspective, we're shearing it. So instead of looking at E values, a Young's modulus, we're going to be looking at G values, a shear modulus. So shear moduli typically are a little lower than E values. That's just how it is. So if I have the shearing stress, I can determine the shearing strain by just dividing by G. So if tau max is TR over J, gamma max is TR over GJ. So everybody okay with that? All right. Lastly, I want to go back to this. Can I see this real quick? Oh, no, you're fine. There we go. So one other very important parameter for torsion, let's go back to axial loads. So I would argue that when we were looking at axial loads, really the two big things we were after is, number one, how much stress do we get? And two, how much deflection do we get? In other words, if I take this bar and I yank on it, we want to know how much it's stretched out, like 0.23 inches or what have you. Well, for torsion, A, we want to know what the stress is, but we also want to know how much does it twist. Does it twist 10 degrees or 12 degrees? And is it twisting too much or not enough or what have you? Usually not enough is fine, but too much is usually the big issue. So I want to go back to this definition for strain. Remember, we had that the strain was proportional to that radius. But we now have a definition for strain. We can say T rho over GJ because we just solved that out. So what I then want to do is I want to see if I can determine the phi value. That phi value is how much it twists. So if I plug and chug, the rho part cancels out. So you can start to see where this is going. This is how much angle change I get in that small little disc, that little slice along the shaft. If I integrate from x equals 0 to x equals L, that'll tell me how much twist I get overall. So one of the things I want to point out, let's say I have a torsional shaft, right? Okay, and I twist it. This is really easy to see with a mock-up like this. This is another observation to make. All right. I have angle of twist is an integral from x equals 0 to x equals L. So if everything's constant, you would agree I would get this, right? That's pretty easy. It's also easy to see from a visual perspective, okay? Hold this, right? Hold this fixed, and then twist this like 180 degrees, okay? So right here at the end, I've twisted 180 degrees. How much have I twisted right here in the middle? Only 90, right? Maybe 45, what have you. The longer the section is, the more twists you get, right? In other words, if I took that same torque and I applied it here, I would only get half the twist. The longer the section is, the more torque you get, or the more twist you get, okay? Everybody okay with that? So how do I determine the maximum angle of twist? TL over GJ. Like I said, I promised you a nice little summary. Here's a nice little summary. So let's look at shear stress. So shear stress, the formula, remember, it's linear. T rho over J. The maximum stress is going to be on the outside, so more often than not, all we care about is this, the TR over J at the end. For shearing strain, all I'm doing is taking these values and dividing them by G, converting stress to strain. As for the angle of twist, that's an integral. Now, just like before, We never need to integrate if the load is constant or in this case, J is constant. So if the section is constant and the applied load is constant, we never need to integrate, so we would just get TL over GJ. As for J values, J for a solid shaft, pi d to the fourth over 32, and for a pipe, it's pi over 32 times the difference of those diameters to the fourth. So I wanted to, like I said, in a nice bow, there's everything that you need. So let me see if there's anything on the next slide. Oh, okay. Is everybody okay with this? I'm gonna leave this up here for a sec. Also, like I said, the textbook might tend to refer to this as I sub P, but it's the same thing. Especially, essentially for when we're dealing with a circular section. I'll be honest, I like to call it J for two reasons. J's a lot less letters than I sub P. I'm lazy. But actually, there's a real reason that I like to call it J, and it's actually for you civil engineers. When you take steel design, in steel, we refer to that constant as J. And the reason why is because I-beams warp. Okay, so in lateral torsional buckling, we have a J value, and then we have a warping constant. I'm not going to make you all deal with that because that's a little above and beyond for our purposes. But for civil engineers, we refer to that term as J because we use I for other things like moments of inertia about the x-axis and the y-axis. So I think it's a little easier when you see J, you're like, they're talking about torsion. So everybody got this? Let me leave it up here for a sec. Okay. A couple other things to point out. If you have constant torque and constant J values, you can just determine phi max with just TL over GJ. And this one's important, okay? I mentioned this like a couple weeks ago, and we really haven't used it, but it's very possible that you'll see this pop up on homeworks and on celebrations, that if you know what the Young's modulus is and you know what Poisson's ratio is, you can calculate G. So it's possible that you have a problem and you're not given G, and you're like, well, how do I do this problem? Well, if you've got E and Poisson's, you can do it. So. Everybody good? Okay. Let's look at some problems. All right. First off, when you see some of these diagrams, you're going to see the dreaded right-hand rule pop up again. Oh, no. Not like you said no IJK. You told us, Dr. Mike, no IJK. Are you really going to do this? No, I promise no IJK, but you are going to see a right-hand rule pop up every now and then. And what I mean by that is this. Here I have a circular shaft. This is a solid shaft, and it's being subjected to a torsion. Now, textbook, and honestly by hand, it's really easy to draw this. A lot of times you will see a torque referred to like this with two arrows, okay, like a double-pointed arrow. And so if you point your thumb that way on your right hand, it indicates we're twisting it that way, okay? So this side is going like this, that side is going like that, so we're doing that to the pipe. Does that make sense? So you're going to see me draw that, and you're going to see that in your book. So I want you to recognize that. Now, I don't think you see it everywhere. Sometimes you see that, and that's fine too. I just wanted you to be aware of that. Okay. So here we have a shaft that has a length of 54 inches. It has it's a steel circular bar. It has a diameter of 1.5 inches. So we know it's steel, so we're going to take the Poisson's ratio to be 0.3, and we're going to take E to be 29,000 KSI, or 29 million PSI. The bar has a constant torque, okay? So we're going to determine the following. If the torque is 250 foot-pounds, what is the maximum shear stress in the bar and the angle of twist between the ends of the bar? And if the allowable shear stress is 6,000 PSI and the allowable angle of twist is 2.5 degrees, what's the maximum permissible torque? This is a very, common type of example for engineers. So has everybody got this? Don't worry, we're going to regurgitate a lot of this data here in a second. Okay, let's start writing down some of the given properties and the given parameters for this problem. All right, let me see. Oh, there we go. So we know that the length of this problem, or this bar, is 54 inches, right? We know that the diameter is 1.5 inches. So if we know the diameter, what can we go ahead and compute? Okay, the J value. I heard somebody say area. Yeah, we can compute the area. There's nothing stopping us, but it's not going to be useful. We're just not going to use the area. We're going to compute it and not need it. What we can compute is J. If we're twisting things, J is what you need. So we're going to compute J, and that's going to be pi over 32 times d to the 4th. Okay? So that's pi over 32 times 1.5 inches raised to the 4th, and that comes out to be what? Inches what? To the 4th, right? Yeah, inches to the 4th. Now, do I have a second on that? There we go. All right. Now, here's another thing. We were also given an E value of 29 times 10 to the 6 psi, and then a Poisson's ratio of 0.3. So using those, I can compute a G value. So that is 2 times 1 plus nu on the bottom. That Greek letter is nu, by the way. So, and that's E up top. So we have 2 times 1 plus 0.3, and then 29 times 10 to the 6 psi. And that comes out to be what? It is still too early for all these calculations, man. So you said 1.12? All right, so I'm going to call that 11,200,000, something like that. Or yeah. And for our purposes, we can keep it like that. I mean, if you're, you can carry your values however specific you want to be. I think 3 decimal values is, going to be fine for our purposes. So this is just us computing the properties that we need for this problem. Now, let's look at part A. Okay, part A for the problem states this. This is going to be pretty plug and chug. It's stating that if I put a 250 foot-pound torque on this shaft, what's the stress and what's the angle of twist? Okay, so first off, let's look at that torque. Does anybody see a problem with a torque of 250 foot-pounds? There we go. We have to convert that to inch pounds. So now let's pop quiz. How do I convert that to inch pounds? Do I multiply by 12 or do I divide by 12? Multiply. There you go. That's 3,000 inch pounds. So make sure you don't mess that or mix that up. Okay. So yeah, right off the bat, make sure you're using consistent units. And that's sort of a point with this problem is, the units are sort of in, different configuration for that reason. So, okay. Now, let's talk about stress. If I'm applying a stress to a shaft subjected to torsion, where's the maximum stress? On the outer edge, the exterior wall. So, therefore, tau max is TR over J, which is 3,000 inch pounds times, now what's R? That 0.75 inches? Because our diameter is 1.5. And then this is 0.497 inches to the fourth. So what are we getting here? So 45.27. Second on that. What are the units? Yeah, PSI. It's a stress, right? So that's another thing. If everything's consistent, like everything's in pounds and inches and all the units are consistent, it's a stress. So it's PSI. So, but if you want to follow it out, I've got pounds times inches squared on the top, and I have inches to the fourth on the bottom. So two of those cancel. I get pounds and inches squared. So, okay. Oops, sorry. Speaking of, let's talk about units here. Now our maximum angle of twist, so our maximum angle of twist is TL over GJ. So 3,000 inch-pounds times 54 inches, and then we have 11.2 million PSI. And if you want to carry out further decimals, you can. I don't think it's going to greatly affect our answer. Over 0.497. Now, I'll go ahead and tell you, when you compute this out, it's going to be a small number, and that's okay. So what are we getting for this? 0.029. Do I have a second on that? We're going to talk about that. We're going to talk about that. First, let's talk about the value first. Is the value right? Okay, all right. Now let's talk about the units. He's saying the units seem a little wonky. They are, but let's follow it out. Okay? So on top, I have inches, I have pounds, and I have inches. Right? On the bottom, I have pounds, inches squared, and I have inches to the fourth. Okay? So on top, I have pounds, inches squared, and on the bottom, I have pounds times what? Inches squared. So there are no units. What are we computing, though? What is phi? It's an angle of twist. So when an angle doesn't have any units, like how do you express the value of an angle with no units? You do it in radians. So when you compute an angle of twist and you plug and chug, it's going to give you an answer in radians. Hence why I was saying it's okay if it's small. Okay, that's fine. How do I convert that to degrees? 180 divided by pi, right? So if you multiply that by 180 and divide by pi, what do you get? .67 degrees. Do I get a second on that? So everybody okay with that? I want you to follow that out, that when you compute a phi value, when you're plugging and chugging, because of the way our formulation, remember we're integrating, like when we defined our circumference, we said that our circumference was 2 pi r. We were already looking at radians from square one. When you plug and chug, that's what this is going to come out to be. So I didn't want you to get freaked out if you get a really small value. Everybody good? All right. So to summarize, this part A is pretty simple. Tau max is 45.27 psi, and phi max is 1.67 degrees. And I can already see right now, like one of the questions I might get is, well, what do you want on a homework assignment, or what do you want on an exam? And I have two answers for that. Number one, if the problem says answer in degrees or answer in radians, then follow the problem. If not, put whatever you want, but make sure that you're indicating it. Like, is it this many radians or this many degrees? As long as it's correct, it's correct. It really doesn't matter what unit system it is. So I'm fine with either one. Everybody good? Okay, all right. Now let's look at part B. Okay, so part B is doing something a little different. Part B is, instead of giving us limits, or instead of giving us like a torque and saying, okay, what's its response, part B is saying, okay, here are some limits. Here is the maximum allowable shear stress. Here's the maximum allowable angle of twist. What's the maximum permissible torque? So what we're going to do with part B is basically rearrange our equations a bit and solve for T and see what we get. Let's handle each of these one at a time, okay? And I don't think we've had a problem directly like this, but I think we have, but this is a good revisit. I think we had one of our earlier examples. We had a couple limits that we had to evaluate. I don't know if it was as expressly indicated as we have here. Does everybody have this? Can I go ahead and move on to the next sheet? I'm running out of pages. We're already on 22 pages of calcs. Just wait to the end of the semester. Like, that's not, like, encouraging. That was a joke. All right, part B. So we know that we have a maximum allowable shear stress of 6,000 psi, and we have a allowable angle change of 2.5 degrees. Now, what I would do is I would do this. I'm going to go ahead and say that that's 2.5 degrees, but it also equals 2.5 pi over 180 radians. Is everybody okay with that? Because when we start plugging and chugging into our equations, we're going to need this in a unitless expression. So I'm going to go ahead and do that. If you want to write down a decimal value, you can. I'm probably just going to leave it like this. Now, let's take each of these one at a time. Remember, our formulas are tau max is TR over J, and we have phi max is TL over GJ. So let's take each of these one at a time. So the first one, I'm going to say that my torque, we'll call it T allowable, is going to be based on that stress. So how do I solve this? I take the J multiplied over, divide by R, so I get tau max J over R. Did I do that right? All right, so plug and chug, I get 6,000 psi. I get a J. What's my J for this? I can't remember. All right. And R, this was 1.5 inches in diameter, so 0.75 inches. So what do we got? Okay, so we got, what'd you get? 3976 PSI? Or no, that's not PSI. What is that? It's a torque, right? So inch pounds. Now, do I have a second on that value? Okay, all right. So that's the first one. Now let's look at the second one, okay? So let's solve based on the second one. So what do? I take my phi max, GJ, and then divide by L, right? So phi max, GJ over L. Did I do that right? You'll see where the values and like what our final answer is going to be here in a second, because I want to talk about that and how we arrive at that. So oh, my pen got away from me there. So 2.5 pi over 180 radians. Now this was like 11,200,000. Right? This is 0.497 inches to the fourth. And this is 48 inches. There we go. I'm making sure y'all are awake. Sorry, I couldn't help myself. He's like, that was mean, Dr. Mike. That really was. All right. So what are we getting for this? Say it again. 44.98. And that's also going to be in inch pounds. Now I get a second on the value? All right, okay. Now, so now we got the math out of the way, let's figure out just what the heck it is we just calculated, because we just plugged and chugged in some values, but I want to make it make sense. Okay, so the problem said I got a shaft and I got two limits. It can't have more than 6,000 psi in stress, and it can't twist more than 2.5 degrees. So I calculated allowable torques based on each of those. In other words, if all I had was a maximum allowable twist of 2.5 degrees, then that's my allowable torque. And if all I had is a maximum allowable stress of 6,000 psi, then the 3976, that's my torque. Okay? Now my question for you is this. Which is the answer? Is it the first one or the second one? It's the first one, right? Here's why, okay? Let's say I put that much torque on the section. I propose that if I put 4,498 inch-pounds of torque on that shaft, that it's going to twist 2.5 degrees, right? That's what that value is. But if I put that much torque on the section, how much stress do I get? Way more than 6,000, right? So this is the only value this is the highest value that meets both of those limits. In other words, if I put this much torque on the section, I'm going to get 6,000 psi, but it's going to twist less than this amount, okay? So that's why I'm selecting this one as my safe value. In other words, T max is 3976 inch-pounds. Or if you like things in foot-pounds, you can say 331.3 foot-pounds, just dividing by 12. If, you know, whatever you want to do. What do you think? Any questions? This ain't bad, is it? It's just plug and chug. Now, what do you, what, I, well, I'm saying that to twist it that much, you need that much torque. And to answer your question, is it reasonable? Yeah, it is, because the material constants that we're using are very representative of steel. I mean, structural steel, its E value is 29,000 KSI. You can pretty much set your watch by it. And so when you compute a shear modulus for steel, it ends up being about 11.2. So that's pretty realistic. So yeah. Now, let's also be clear. I mean, what it can handle is usually well beyond this. I mean, we put a stress limit on this of 6,000 psi, but honestly, steel can handle a lot more than that. But another point worth mentioning, and this is sort of gleaned when you just look at the E values and the G values, steel's got a little bit more spring when it's in shear than opposed to when it's being loaded normally. But that's not unique to steel. That's pretty much just about every engineering material that you're going to see. I don't want to say every one, but common ones, I'll say. Everybody okay with that? This is good stuff. These are good questions. All right. Okay, all right. Now, this one ramps it up a bit. I'll be honest, we're probably not going to finish this example, but I do want to get some of the property calculation done. Now, this one, so that you're aware, first off, there's no calculus in this one at all, okay? No calculus, okay? Because for calculus to be the case, first off, you have to have a shaft that has a varying diameter or a varying shape. That's not the case because we have a shaft with a constant J. It has an outer diameter of 40 millimeters and a wall thickness of 5 millimeters, so we don't have to worry about that. Now, as for the torques, well, technically the torque isn't the same across the shaft, but we can break it up into segments where the torque is the same. So for instance, if we're looking at angle of twist, well, we can just figure out how much each segment twists individually and just add that up, okay? So everybody okay with that? All right. Now, we have a shaft that's experiencing a boatload of different torques. We have torque 1, torque 2, and torque 3, each going in different directions in different regions of the shaft. So the shaft is, experiencing some differential twist in it because of these torques. Now, we've got these lengths, LBC and LCD, that each have different lengths. So different lengths, different torques, so on and so forth. One thing to point out about the torques is that they are self-balancing. And what I mean by this, it says here the torque is driven by gear C, okay? So what's going on in this shaft is gear C is wanting to rotate the shaft this way, okay? So it's supplying 450 Newton meters of torque. Gears B and D are resisting it, okay? So they're resisting it by a value of 275 and 175, okay? So right off the bat, what's 275 plus 175? 450, right? So sum of torques is 0. In other words, I got 450 Newton meters of torque going this way, and in resistance, I have 450 going this way. So I want to just right off the bat say that sum of torques is equal to 0. So what we're going to do on this problem is determine the maximum shear stress in each part and the angle of twist between the gears, okay? So come on. Come on. All right. So we're not going to finish this problem today, but I at least want to set up some of the calculations and make a couple points in regards to units, okay? Now, first off, let's look at J values. This is a pipe, okay? We know that the outer diameter is 40 millimeters, or I should call it just J value because there's just one J. 40 millimeters, and we have a wall thickness of 5 millimeters. So in order to determine J, the property of that section, what do we need? Say it again? We need the inner diameter. So how do I determine the inner diameter if I have the outer diameter and a wall thickness? Minus two thicknesses, a thickness this way and a thickness that way, right? So I think I can do this one in my head. 40 minus 10 is 30. All right. And so now that I've got an inner diameter, I can say J is pi over 32 d outer to the fourth minus d inner to the fourth. So what do we got here? I can't do that one in my head. I'm not that good. Remember, that's to the fourth. It's not squared. So it's going to be a big number. It's okay. 172,000. And that's millimeters to the fourth, right? Okay. Now, some other values that we were given. We know that the length of BC is 500 millimeters, and the length of CD is 400 millimeters. We know that G for this problem is 80 gigapascals. Now, I think it's probably a good point right now to go a little bit off on the side and talk about units, okay? Because we got SI units going all over the place. So I want to make two notes about units, okay? So let me sort of put my little thought bubble over here. So note, okay? One thing that, and you can derive it and figure out, but if you take a kilonewton and you divide it by a millimeter squared, you can follow it out and you will get a gigapascal, okay? So that's a little shortcut for metric, that if you have kilonewtons and millimeters squared together, that your stresses are in gigapascal. And the reason why I mention that is because sometimes your allowable stresses might be referenced in megapascals, and instead of trying to convert everything, if you just convert that to gigapascals, then everything meshes together well, okay? So that's point one. Another point, this one's kind of nifty, but a Newton meter and a kilonewton millimeter are the same thing, okay? Because to go from newtons to kilonewtons, you're dividing by 1,000, and from meters to millimeters, you're multiplying by 1,000. So it's the same thing, okay? So the reason I mention that is because when you have a torque B, torque C, torque D, and they're in Newton meters, just write them in kilonewton millimeters, okay? Because you know it's going to match, okay? So I'm going to go ahead and write that out. So TB, TC, TD, and I don't remember the values right offhand. So 275, 450, 175. 275, 450, 175, and that's kilonewton millimeters. Okay. All right. Any questions? It's 9:12. We're not finishing this problem today, and so what I think I want to do is this. I want to hold off on actually diving into the meat of this problem until Thursday, okay? What we're going to do on Thursday is this. We're going to finish this problem, then we've got two more topics in torsion that we need to investigate. One of them is how do you handle torsion for indeterminate structures, okay? Like indeterminate torsion. That's point one, which I think you can probably figure that out, you know, because it's going to be very similar to what we did with axial members. But the other thing that we have to deal with is something unique to torsion. That's what we're going to handle next time, and that's power-torque relationships. In other words, if I apply torque to a section, let's say it's a shaft meant for transmitting power, how do I transmit that? How do I develop that relationship between power and torque? And then there's unit conversions in there with horsepower and things like that. But that's topics for discussion on Thursday. So don't forget, Thursday, homework number 2, turn that in, bright and early. We'll give you homework 3 on Thursday. It's due the following Thursday. That Thursday we have exam review, and then on the following Tuesday we celebrate. Sound good? All right. That's all I got. See you all on Thursday. And some of you at 2 o'clock.